Hello, in this video we will be looking at section 9.5 where we focus on the product rule and to a lesser extent the quotient rule. The product rule is useful anytime you have a function f of x which could be thought of as the product of two separate functions. So you have one function, maybe u of x, another function v of x, and as long as you could imagine that f really is two separate functions, then the product rule would apply. For instance, if we look down at this first example, we have our first function, and then we have our second function, and because they're being multiplied together, the product rule is going to apply. Now, what does the rule say? It says if you want to take the derivative of the function, then the way we do this is we start with the first function multiplied by the derivative of the second function, and then we add on the second function times the derivative of the first function. Now, there's a nice diagram that I like to use to visualize the way that this rule works. What I think about is I'm going to give myself a 2x2 grid here. And I'm going to start with writing down what u is equal to, and then I'll write down what v is equal to. And right underneath these, I'm going to compute their derivatives. So we can compute u prime and we can compute v prime. Now, once you have these written down, you can construct the product rule by multiplying along the diagonals. So notice it says u times v prime, and that's what we get when we multiply along the first diagonal. And then if we multiply along the second diagonal, what we get is v times u prime, which is what the product rule shows. So in these notes, when I apply the product rule, I'm always going to organize myself in this table first. I'm not going to be writing down this formula at all. I'll just organize myself in the table and then multiply along the diagonals, and then we will add the two, whatever the two things are. Okay, before we get too involved in this, let me discuss why we need a product rule to begin with. So I'm going to move those notes down to the bottom, and let's ask the question, let's suppose that you know that f of x is equal to something like 2x squared times 3x cubed. Now, this is something that you could very easily use a little bit of algebra and multiply together. 2 times 3 would give us 6, and then x squared times x cubed would give us x to the 5th. So if you wanted to compute f prime, you would very naturally just focus on 6x to the 5th. The derivative of that, you take the 6 times the 5, would be 30, reduce the size of the exponent by 1. So we should end up getting 30x to the 4th. What would happen if I tried to just take derivatives individually? So I'm going to look at this first piece, take its derivative, look at the second piece, take its derivative. So I'm going to take derivatives. And I hope that this quick example will illustrate why we have to have a separate rule for products. If you take the derivative of the first piece, you get 4x. If you take the derivative of the second piece, you would get 9x squared. And when you think about this, we know that the derivative of f should be 30x to the 4th, but if we only took the derivatives separately and then multiply them, there's no way that this would actually equal the answer that we need to get. So the point of this little example is that just taking derivatives doesn't work. Okay, having seen that, let's go back and look at the process that we actually have to use. Let's look at our first example. I'll leave the rule up there at the top of the screen. First of all, we would like to find the derivative dy dx and simplify. Now, I've already done the very first step, which is I have to look at the function and realize that it's actually two separate functions being multiplied to each other. But once I realize this, then we can actually apply the property. So I'm going to write down u is equal to x cubed minus 3, and I'm going to write v is equal to x squared minus 4x plus 1. Now from here, right underneath, I'm going to write u prime. Let's compute that derivative. 3x squared plus 0, so just 3x squared. And then we'll compute v prime, which is 2x minus 4. Once you have computed those, I'm going to put them in this little box just for the visual. And then my purpose in writing this box is that I know I'm going to have to multiply along the diagonals. So I'll do that highlighting, and let's go ahead and start writing our derivative. So we wanted to compute dy dx. Remember, this is just notation that means compute a derivative of y. So then it's going to be, let me trace out this diagonal first. I'll start with u, then times v prime. Gives me x cubed minus 3 times 2x minus 4. Then we add on what we get when we multiply along the second diagonal. Now, there's nothing important about the order of these two. You can either write this one first and then this one, or you can write u prime first and then v. And in this instance, I like to have 3x squared out in front of the parentheses, so I'm going to choose to write it that way. Now, having done this, we have successfully applied the product rule that we see up there. We've done all of the calculus in this step, but we still need to simplify, so we're going to use a little bit of algebra that's going to help us just reduce this. I need a little bit more room here, so let's go down. This is equal to, we're just going to start by distributing. That'll be 2x to the 4th minus 4x cubed. Continue distributing. This is minus 6x plus 24. Then we'll distribute in that second set of parentheses, and we should get plus 3x to the 4th minus 12x cubed plus 3x squared. Okay, we have a lot of like terms, so I have things that have x to the 4. That should be 5x to the 4th. And then I have a couple of pieces here that have x cubed, so I'll have minus 16x cubed. Nothing else is a like term, so I'll just write these in descending order with 3x squared minus 6x plus 24. All right, this is my final simplified derivative, so we'll call this dy dx. Now, I want to point out there were other methods that we could have used to compute this derivative. So from the beginning, we noticed that we really have two separate functions being multiplied to each other. If you wanted to actually multiply the initial problem out, you could distribute the x cubed into parentheses, distribute negative 3 into parentheses. You'll have 6 terms, then combine all of your like terms. And then what you would have, if you did that, I'm not actually going to do this, but you would have like x to the 5th plus a bunch of stuff, and eventually you'd have a minus 3 at the end. If you took the derivative of this thing, what you would get is you would get our final answer here. Now, it would take a little bit of time, so we're not doing that right now, but I'm just indicating there is another way to approach this problem. However, that's kind of specific to this example. There are definitely calculus problems that do not have alternate methods of computation, so it's nice to get practice with this product rule so that you'll be able to use it when you're in a situation that doesn't have a secondary method. Part B, let's find the slope of a tangent line at a given point. All right, so I guess I should label my work a little bit better. We just did part A. Let's go ahead and do part B. We want a tangent slope. What we need to remember is that the purpose of a derivative can mean a lot of things, but one thing that a derivative means is it will compute slopes of tangent lines for you. So what we would like to do is we would like to evaluate our derivative at the given point. So let me say at the point 2, negative 15. Now, there is very common notation, like if I said compute f prime of 2, that looks like it means we need to put 2 into the f prime function. Well, here, this is not called f prime because my original problem wasn't called f. My original problem was called y, so then the derivative was dy dx. So we want some notation that just means put 2 into this thing. The standard notation, so it's not called f, I'm going to get rid of that, dy dx evaluated at x equals 2 would be the standard way of writing this. And all this notation says is it's telling the reader, which would be you if you're watching this video, I have a derivative function, I'm planning to evaluate it at the number 2. Okay, so just plug 2 into the function. Let's go ahead and see what we get. Okay, when I plug it in, I end up getting negative 36, so this is the slope of a tangent line at the given value. Now, the question that was written does not ask for a tangent line, but it's a good idea to review that idea. If you actually needed to find a tangent line, my preferred method is using this point slope form, y minus y1 equals m times x minus x1. And we can just plug all of our information in there. So it's y minus, okay, I go reference the point, it has a y value, so it'll be y minus negative 15. Y minus a negative 15 just means y plus 15. This is equal to negative 36 times x minus 2. And that would be the tangent line if the problem had asked for a tangent line. Let's go ahead and do part C now. So in part C, give ourselves a little bit more room, we want to find the instantaneous rate of change when x is equal to 2. We don't need much more room, because what you should realize is that instantaneous rates of change, that's synonymous with derivative. So if you've already computed a derivative, what does a derivative tell you? It tells you slopes of tangent lines. It also tells you instantaneous rate of change. So I'll write the words out. Instantaneous rate of change. It's the exact same thing. It's your derivative evaluated at the point that they picked, so at x is equal to 2. So if we put 2 into the derivative, we've already seen that we get negative 36. Let's go ahead and look at the next example. All right, here, what we're looking at is we have a function that's very clearly a product of 2 functions. So we have one function being multiplied by another function, and this time we would like to find the derivative, but we're not going to actually simplify. So let's get at it. Because we have identified this as a product of 2 functions, I'm going to write them down, u and v. U is going to be 4x cubed plus 5x squared minus 6x plus 5. Actually, let me give myself a little bit more space for my v. V is going to be equal to x cubed minus 4x squared plus 1. All right, we can then think about what their derivatives are. For u, we kind of do this same process using the power rule. We take the exponent multiplied by the coefficient, then we reduce the exponent by 1. Continue on with that process, and you should find that your derivative is 12x squared plus 10x minus 6. Then the derivative of v is going to be 3x squared minus 8x, and that'll be it. Put these these 4 things in a box together, and then you don't have to use a highlighter, but I like the visual of like having that highlighter on the page. We are now ready to compute f prime. F prime is equal to, we will have to write pretty small if we want to get this all in one line. It's going to be 4x cubed plus 5x squared minus 6x plus 5 times 3x squared minus 8x plus, so what we just did there was we multiplied along that first diagonal, just listed what we got, and then it's always going to be added to what we get when we multiply along the other diagonal. So the other diagonal was 12x squared plus 10x minus 6 times x cubed minus 4x squared plus 1. All right, now the instructions say do not simplify, so we're just going to leave it like this. And this is the derivative. It's kind of messy, but it is what it is. All right, part B. Find the slope of the tangent line when x is equal to 1. Well, we know that slopes, I'll write the word tangent. The slope of a tangent line can be computed from the derivative, so I'm going to take f prime and I'm going to put 1 into it because they told me the x value was 1. All right, now again, we're just putting 1 in here, so I'll pause the video, write it out, and let's see what we get. All right, once you plug that either in your calculator or you can do it out by hand, we should find that our slope is -72, so that answers part B. Then in part C, let's write the equation of a line that's tangent to the graph at the point. All right, so for my tangent line, I would like to use this same point slope format. We know some of the information, and we are missing some of the information. So you only need 3 pieces of information to have your tangent line. You need a slope, you need an x value, and you need a y value. We computed a slope already. They are giving us an x value, so the only thing we don't have is we don't have the y value. Let's fill in what we do know, though, and let's go compute what we don't. So y1 is going to be equal to, well, the way you would compute a y value is you would put the x value into the function. Now the function's off the screen right now. Actually, let me just go show what it is. There it is. So we're going to put 1 into that original function, and let's see what we get. Turns out we get -16, so y minus -16 should end up being y plus 16. And we have a slope of a, sorry, not a slope, but we have an equation of a tangent line. All right, so that finishes up our examples about the product rule. Next, we're going to look at a quotient rule. Now, just as a disclaimer, in a brief calculus class, we really don't focus much at all on the quotient rule. We really kind of emphasize the product rule more. But just so that these notes are thorough, I thought I would include some information about the quotient rule. Okay, and I need to start by correcting a typo. Quotient means divide, and this is certainly not divided. So I'm just going to rewrite that part of it. My apologies. I just don't have time to go back and recreate this. All right, what it should have said is if your function is the quotient of 2 separate functions, where u is in your numerator and then v is in your denominator, then the derivative of that function could be given by this expression. So you'll notice a lot of the pieces look similar. We have v times u prime, and we have u times v prime. This time we are subtracting, though, so the order of these is going to be important. These 2 have to be first, and then these 2 have to be second, and you're dividing by the denominator squared. So there's a lot of kind of pieces to keep track of, which makes this a fairly difficult formula to memorize. What I'm going to do, not that in my class that you would have to have this memorized, but I'm going to give you a method if you're watching this and you do have to have this memorized for one of your classes. I'm going to call the numerator the high part of the function and the denominator the low part of the function. So, of course, high is on top, low is on bottom. The reason we do this is so that we can sing a stupid song that hopefully helps you remember the formula. Okay, and it goes like this. Well, it's low d high minus high d low over the square of what's below. That's the quotient rule, and now you know it's low d high minus high d low. All right, I'm not a trained musician. I hope that was not terrible. And if you don't have to have it memorized, don't listen to it again. But let's go ahead and apply this in just one example. So I'm still going to call these functions u and v. Our numerator is 2x cubed. Our denominator is 3x to the 4th. Plus 2. We haven't taken its derivative yet. And then we're going to take the derivative, so then u prime is going to be 6x squared. V prime is going to be equal to 12x cubed. And then that means that the derivative of c is going to be equal to, okay, so if you are thinking about the stupid song, it's low d high minus high d low. So we start with the low function, then d high. Now we've written that over here, so the derivative of the high function is right here. 6x squared minus low d high minus high d low. So minus high d low. Oh, sorry, I started writing the wrong thing. It's the derivative of the low function, 212x cubed. And then this is over the square of what's below. 3x to the 4 plus 2. That was what was below, but we squared. Okay, so this is it. We would reduce this. Let's go ahead and reduce it. They usually can't reduce very much, but you do want to distribute this into parentheses. So that would be, what is that, 18x to the 6 plus 12x squared. You would also multiply these two things together, so let's do that. So it'd be minus 24x to the 6. So we do have a couple of like terms. 18 minus 24, I believe, is 6x to the 6 plus 12x squared over 3x to the 4 plus 2 squared. Now this is our final answer. You can only simplify this if you could factor something out of your numerator and then have a factor that matches that factor in your denominator. Now in your numerator you can certainly factor it. Like I could factor a 6x squared out of my numerator. That would leave me with x to the 4th plus 2. But then we just noticed that this does not match this exactly, and this also does not match this exactly. So to check to see if it's reducible, you factor out, but then if this doesn't actually reduce, then there's no need to even write the factored version. We can just leave that expanded version as our answer. All right, so hopefully this context of the quotient rule is a little bit helpful for you if you need to use it for your class. But if not, then certainly those examples about the product rule are going to show up in pretty much any calculus class that you could be taking.